Let's start by considering this message passing algorithm. If this program is executed under sequential consistency, once it is terminated, the value of local register R2 is going to be 5, and this post condition can be established. If the same program is executed under C11 weak memory model, we only be able to establish this weaker post condition. This is the result of the weak behavior allowed by the memory model, where the writes to variables D and F can be observed by thread 2 in any order. To regain the expected behavior, we introduce additional synchronization in the program. In particular, the write to F by thread 1 must be a releasing write, and the read of F in thread 2 must be an acquiring read. Now that we have the program with correct synchronization, we can establish the stronger post condition again if we have the right tools. Our work introduces an operational semantics for our C11 RAR fragment. We have developed a proof method based on the Owicki-Gries proof calculus, keeping all of the original proof rules, including the non-interference check, unchanged. Our technique introduces a set of basic axioms to cope with memory accesses. We have also developed a simple assertion language that can describe the current configuration of the weak memory state. The assertion language allows us to annotate a message passing algorithm like this. This is the negation of a possible observation assertion. It says it's not possible for thread 2 to see value 1 for variable f. Note that this assertion is talking about the view of the other thread. This one is a definite observation assertion, meaning that thread 1 is definitely seeing 0 for D. After the execution of line 1, the assertion says that the thread is definitely seeing 5 for D. Now look at thread 2. This assertion is a conditional observation assertion. It says if an acquiring read of thread 2 reads value 1 for F, then the thread will synchronize with the thread that wrote 1 to F, and its knowledge of D will be transferred to thread 2. So, if the acquiring read on line 3 reads 1, then we know that if the thread reads D, it will certainly observe value 5. Our method has been formalized in Isobel, and we have verified a number of examples, including non-trivial Peterson's mutual exclusion and read, copy, update algorithms there. We have recently extended the Isobel's standard Owicki-Gries theories to support our operational semantics and the C11 memory accesses. In addition to the 3 assertions we used in verification of the message passing algorithm, our language supports other types of assertions that are useful in verification of various properties. For instance, for verification of Peterson's algorithm, we use another assertion called covered writes. For RRC litmus tests, we used another kind of assertions that describes the ordering between different writes to a variable. Our extension to the existing Owicki-Gries theories increases the usability of our approach, as the user can simply invoke the existing verification condition generator and it automatically generates all the proof obligations for local and global correctness. For example, the verification condition generator results in 258 proof obligations for Peterson's algorithm. While some interactive proof is required, the proof is relatively compact and readable. For smaller programs, it's even simpler, and automatic provers can discharge all of the generated proof obligations. For more details on the operational semantics and the proof method, please have a look at our ECOOP paper. And for details of our Isobel extension, see this report.